Welcome to the lecture series of the College of Science. My name is Joaquin Ruiz. I'm the Dean of the College. Last week we had a lecture series which was really extraordinary in itself. It was about mind and brain, and it was all about what makes us humans. This lecture series now on cosmology is what makes us. So I hope you enjoy it. Today's speaker, I am really proud of introducing Chris Impey, although many of you may know him. Before I introduce Chris, of course, I think we have to recognize again those folks that make it free for the rest of us, and those are the sponsors of the lecture series. But let me now introduce you to Chris Impey. Chris is a university distinguished professor whose research interests are observational cosmology, gravitational lensing, and the evolution and structure of galaxies. He has 160 refereed publications and 60 conference proceedings, and his work has been supported by $20 million in grants from NASA and NSF. He has won 11 teaching awards, and he has been heavily involved in curriculum and instructional technology development. Chris is past president of the American Astronomical Society. He has also been a National Science Foundation Distinguished Teaching Scholar, a Phi Beta Kappa Visiting Scholar, and the Carnegie Council on Teaching's Arizona Professor of the Year. He has written over 30 popular articles in cosmology and astrobiology and co-authored 2 introductory textbooks. He is the author of 2 popular books, The Living Cosmos and How It Ends, and in 2009 he was elected Fellow of the American Association for the Advancement of Science. In addition to all of this, instead of sleeping, Chris regularly teaches cosmology to Buddhist monks at the monastery in the Himalayas, has played ping pong at Mount Everest Base Camp, and I have to warn you, his Scottish accent emerges after drinking single scotch. Chris.
Okay, I'm really pleased to be here. So I want to start with history. Guy gave some amazing and beautiful story of the philosophical and the religious traditions that underpin our ideas of the universe. I'm going to give a little more history leading up to the idea of the Big Bang. And the fundamental dichotomy in this subject is a profound issue that it's easy to understand. It's the distinction between whether the universe is finite or infinite. And that's either in time or space. And worrying about this is essentially what cosmologists do. Normal people get up and they worry about paying their mortgage and paying the college bills. Cosmologists, people like me, get up in a cold sweat worrying about whether the universe is infinite or not. Does the universe go on forever, or does it have a limit? These questions have been asked for centuries. Plato's colleague Archytas said, imagine a warrior with a spear at the edge of the universe, and he hurls his spear swiftly. Do you imagine that it goes forever? And into what? Or does it hit something or bounce back? And in that case, what's the limit? So you can see either way there's a bit of a problem. It's either infinite, and what's all that about, or there's an end, and what's the end, and what's beyond the end. And cosmologists wrestle with the same questions, and I'll attempt to partially answer them today. When Copernicus replaced the geocentric model, with the heliocentric model, it was a revolutionary move. The word revolution in our modern sense of it as violent political and social upheaval refers to Copernicus's book on the revolutions, because what he did was not just astronomical, it was a revolution, a profound social revolution. You can imagine also how difficult it was when beyond that, in the mid-16th century, Thomas Digges extended the celestial sphere to innumerable stars, going off the page in every direction, infinite numbers of stars. This was an incomprehensible idea. It got people into trouble. This is the statue in the Campo de Fiore in Rome of Giordano Bruno, who was burned at the stake as a pertinacious and impenitent heretic by the Catholic Church for not only believing in an infinite universe, but believing that those innumerable stars had planets around them with life forms on them and perhaps people. And this was too much to bear. Cosmology is a shifting landscape. The next venture towards the infinite was Isaac Newton, who postulated an infinite universe, infinite in extent, in time and space. And this was followed by Wright, who imagined infinite inhabited worlds in this universe. It's still a difficult concept, and it's difficult conceptually. If you were in a large forest, every sight line through the forest would end in a tree. In an infinite universe, every sight line must end on a point of light, whether it's a star or a galaxy. Since the light from each star diminishes as the square of the distance, but the number of stars rises by the same factor, logically, the night sky should be bright as the daytime sky in an infinite universe. This was a paradox that Newton never resolved. Not only infinite in light, but infinite in gravity too, since that's an inverse square law. So it took longer to learn how the universe works and to resolve Olber's paradox, which, to cut to the chase, is resolved by the finite age of the universe and the fact that it is expanding. Our sense of the universe evolved through the time of Herschel, making a catalog of fuzzy objects in the sky. Another dichotomy arose as an argument over whether the Milky Way, the system of stars we inhabit, was the whole universe, or whether there were other island universes, systems of stars like our own. Herschel managed to map out the Milky Way and knew it was vast, perhaps 100,000 light years across. But at the turn of the 20th century, two very different ideas were in play. In one of them, the fuzzy nebulae, including the Andromeda Nebulae, the easiest to study with big telescopes, were hypothesized to be distant systems of stars like the Milky Way, perhaps hundreds of thousands or millions of light years away. The countervailing model, which was actually accepted through the beginning of the 20th century, said that these fuzzy patches of light were just regions of star formation within our own large galaxy, which was the universe. This was resolved by Edwin Hubble, who made the breakthrough discovery by measuring the distance astronomically to the Andromeda Nebula and a few dozen other galaxies for the first time. The method he used involved isolating variable stars within the body of the galaxy and recognizing that they were identical to similar variable stars in the Milky Way. Nature provides a linear relationship between the absolute brightness or flux from these variable stars and relates it to the period. So by measuring the period of variable stars in Andromeda, comparing them to local examples at known distance, he was able to show that Andromeda was several million light years away. It was an external galaxy. And by the end of his career, he had extended the size of the known universe by a factor of 1,000, from a few 100,000 light years to a few 100 million light years. That's the Hubble revolution. The second revolution is to come, that of the expanding universe. But before going any further in talking about a vast universe, let me remind you, as Guy did last week, that cosmology involves assumptions. We don't know everything. The first assumption, very profound, is that the universe is in fact comprehensible. It's not necessarily the case. In fact, it's difficult to keep the universe in your head. Another assumption is that the universe obeys physical laws. It's a thing that has been found magical to scientists and mathematicians, that the universe is so well described by simple and sometimes complex mathematics, and by a very small set of physical laws that seem to apply everywhere. It didn't have to be that way, but it seems to be that way. These physical laws remind us that our venture into the universe is incomplete. We don't know where this will end. If we simplistically imagine that the universe, nature, consists of things that happen and things that don't, things that are and things that aren't, the theory we have, being modest, describes some subset of the things that actually happen. It's not the theory we want. The theory we want is the theory of everything, a theory that describes everything that actually is in the universe. But the danger, of course, is we don't know how to get there, and along the way, we might, in our overambition, end up with a theory of too much. And how would we know the difference? Another way of looking at this, and maybe a little more profound, is the fact that we're bounded actually not by our science, but by our imaginations. And our imaginations are very supple and very impressive. So there are the set of things, for example, that are possible that don't actually happen. That includes everything that happens in the universe, plus some things that break no law of nature, but don't actually happen. And if you wonder about the things that you can imagine, the imaginable things hopefully include all the things that do happen, but maybe not all of them. Almost certainly include a lot of things that are possible, but not all of them. And includes a lot of things that just don't happen, but they're fun to think about. Once again, how do we bound our imaginations in a universe that has not yet presented us with all of its phenomena? We also assume that the universe obeys very simple laws that says effects have causes. You have to think a bit to realize how incomprehensible the universe would be if causality did not operate at some level. Now note that this does not imply determinism in the universe. Laplace famously caricatured Newton's law of gravity by implying that if we knew the positions and velocities of every particle in the universe, we could predict the entire future of the universe deterministically. Science is not deterministic, but causality is a foundation stone. Without causality, events could precede causes. Things could move backwards and forwards in time, and we know that that is extremely tricky. We make another assumption that is improperly tested by modern science, which is that the laws of physics are the same everywhere. We do know that the cosmological principle, which is the underlying assumption that the universe is the same in every direction and every location, is true in the sense of every direction. Here, looking across the sky, we see roughly equal numbers of galaxies in each sightline. But testing it in location is impossible because of the finite speed of light. If the speed of light were infinite, we could see the entire universe as it is now, laid out before us in its wonderfulness. But the speed of light is finite, and that leads to a very interesting issue, the issue of ancient light. Now, cosmologists turn the lemons into lemonade, and the fact that light has a finite speed becomes an advantage, because it means that distant light is old light. The light that you see reflecting off me from the stage lights takes maybe a nanosecond to reach your eyes. You can't detect that difference. You probably remember the little time delay when people talk to the astronauts at the moon. That's about a second. If you're talking about the sun, and some evil alien civilization squashed it into a black hole and extinguished its light, it would be 8 minutes before we were the wiser, because that's how long it would take that information to reach us. And it actually makes no sense to ask of nature, what is the sun doing now? What is Sirius doing now? No, you have to be patient. You have to wait those 9 years for the light of that bright star to reach you. And by the time you're in the extragalactic universe, those light travel times are becoming interesting. Far longer than a human life. Even the nearest galaxy is a few million light years away, which means we see it as it was in the past. And at the limit of our telescopes, which I'll get to, they become time machines. And that's an extraordinary thing to be given. A final assumption is that our location is not special in the universe. And the more general cultural way of saying that is that we are not privileged in any way. I mean, occasionally it's hard to get over the fact that we feel privileged, but the Copernican revolution, if it's telling us anything, is saying, get over yourselves. Just get over yourselves. You're not that special. You're not that important. Starting with the Copernican revolution itself, we have found that we are not special in our location in our galaxy, that our galaxy is not special in its location in the universe. As I'll mention, we found that we're not even made of the stuff the universe is made of, and the universe we occupy may be one of a larger set of universes. And our biology may not be unique. There's really nothing that might be special about us in a cosmic sense. But this idea of light travel time is critical to understanding how the universe started, because it means to look at how the universe started, all we have to do is look out further and further. And so we have the nearby now, we have the realm of the stars, which is quite recent, maybe human lifetimes. We have long ago galaxies, and for the universe itself, it's ancient. It's looking back to the dawn of time. And now, you thought you were going to get away with just being participants here. We're going to have some audience participation. Yes, you are part of the show. You all got a card. Don't be scared. It's quite harmless. We do this all the time. You have a card. Okay, there is one way to screw up. Don't fold the card so the white points outwards. So you can fold the card, the piece of paper, in half and then half again, and it doesn't matter in which order you do the halves and half again, as long as the colors are pointing outwards. And you will have made a quadrant piece of paper, which with one fold you can put whatever A, B, C, D you want in front. And so I'm going to ask you a question, and you're going to vote, and the way you vote is by putting your answer facing me. Don't put the answer facing you. You know what your answer is. You don't need to remind yourself. If this is my answer, I point it to you, and you point it